going to be hard to see, so if there's a textbook in front of you, I suggest that you be looking at that when we're talking about this. So what we're going to do is have 1, 2, 3, 4. Then going across the bottom is 5, 6, 7, 8. So we have 8 different steps in this mechanism. There's more, but we want to concentrate on these 8. And so what I'm going to do is label this as 1, 2, 3, 4, 5, 6, 7, 8, just as a means of being able to talk about a particular one. So let's go to step number 1. We look at step number 1, and we see here's our catalytic triad, and you'll see the yellow bonds, which represent hydrogen bonds in this particular case. We have the enzyme and the substrate separated from each other, but the substrate is trying to go in. And this is this cavity, which represents the substrate binding site. Step number 2, what happens? We now see that the enzyme is bound to it, and notice that R1, the side chain, the first residue, is bound within the substrate binding site. And this is a nice example of how the substrate binding site is not going to be the same location as the catalytic site. They're not the same, but they'll have to be the same thing. All right, so now what happens, we can see the proton, we pull this way, we see the oxygen becoming more nucleophilic, and it's going to attack that carbon, which at the end is going to be deficient in electrons at the total positive charge. So this now becomes our enzyme substrate complex. The next step is that we're going to now attack. You see we're attacking the oxygen to the carbon. At the same time, we're going to stretch out this oxygen into this oxyionic hole. And we're going to start attacking the nitrogen on the proton of the histidine starts attacking the nitrogen of the peptide bond. If we take a look at this, we should be able to recognize this as a transition state because of the unequal bond numbers and bond lengths and orientation you see within that molecule. Whereas we look here, we'll see that that's fairly stable chemistry. So it's not surprising that this is an intermediate and this is a transition state. We keep proceeding further down to the next point. Again, this is going to be an intermediate because everything is normal chemistry. And we'll see what happens. The bond between the carbon and nitrogen has been broken. The proton, which was sitting on the histidine, which originally came from the serine, notice this hydrogen migrating over here, so now it's sitting on histidine, and histidine gives it to the substrate, breaking that bond, and so this is going to leave as one of the products, taking away the proton that was originally part of the enzyme surface, leaving behind a covalent linkage between the serine and the remainder of the substrate. Go across the bottom now, we don't go to the top, go across the bottom. Now we bring in the water. Water is going to enter. Notice it's hydrogen bonding to the nitrogen. And this is going to make this oxygen what? Make it a nucleophile. It's going to attack the ester linkage that we see. Going up through here, again, a transition state. The oxygen is being pulled into this oxyionic hole. We're stretching out. We have a tetrahedral, or at least a 4-bond-centered carbon. And now you see the proton, which is on the water, being transferred to the histidine. At the same time, we break the bond between the oxygen and our carbon. We now have this pretty much back, because now the serine has its proton back. It's not the same one, but it doesn't matter. And here is the other remaining product, which now is going to dissociate away from it in the final step, leaving behind the enzyme. Please notice that this is exactly the same as this. Remember, enzymes cannot be permanently changed. Even though they can participate temporarily in the reaction, they must go back to the original state. And you see that is clearly here. Okay, so let's go through the mechanism we have so far. Acid base, covalent catalysis, intermediate formation, proximity effect, transition state stabilization. what do we see? Well, first of all, I hope you realize there's a parallel between the two sides. And this should look pretty much like this. And this should look like this. And this one will look like that. So you can see there's also sort of two parallel reactions going on simultaneously. Remember, the transfer of a proton within the enzyme is not acid-base. However, once we take this proton and transfer it to the product, that is acid-base catalysis. We have acid-base catalysis going on here, and it finishes here. Somewhere here, we have the proton transferred from the substrate, water is a substrate, to histamine, and it's finished at this point in time. The fact that it ends up on serine, that's not part of acid-base catalysis. So it's done by this particular acid-base. Covalent catalysis, remember we have this oxygen, which is very nucleophilic. It's going to attack the carbonyl. This formation of the bond between the oxygen and the carbon form a stable covalent bond, forming a bond. That's covalent catalysis. Same thing's happening over here. We're taking the substrate and we're going to attack it this way. Again, that's covalent catalysis. Remember, the substrate to substrate, it doesn't have to involve the enzyme per se. And then this gives rise to the product. So that's covalent catalysis. Intermediate formation, this is an intermediate, that's an intermediate, that's an intermediate, and that's an intermediate. So we have 1, 2, 3, 4 intermediates shown in this mechanism. Proximity effect. Proximity requires two things. It requires limitation of rotation and translation. Please notice, as soon as the substrate binds to its binding site, it can no longer move. It can rotate, it can spin. So we're getting a partial proximity effect at this point in time. However, once we get to this transition state, you'll notice that there's no spinning involved. This is being pulled in this direction, being pulled in that direction. It's only one orientation. So here we have a full proximity effect going on. It's still limiting rotation, translation limit, so that's still partial. Still have it over here. But you notice now the water coming in, that's going to be start held into position. So when it attacks this way, again, we eliminate both rotation and translation. Full proximity effect. And it disappears as we go on. One more to go. Transition state. So we look at our transition state right here. Please notice that we have two hydrogen bonds here, and we have one here. How many do we have here? 1, 2, 3, 4, 5, 6. Wow. You see, there's a greater interaction of the substrate, or what's left of the part of the substrate with the transition state. That's how it's being stabilized. Same thing happens over here. We have two on this side. We have two over here, and 1, 2, 3, 4, 5, 6 over there. A greater interaction of the substrate or the transition state with the enzyme. It stabilizes it, decreases it. So you can see how rich this example is in terms of having all of these different kinds of mechanisms going on. Next slide. Okay, there's a video that probably useful to look at in addition to this video, which talks about it. So let's go through it as quickly. So here's the substrate coming in. R1 is going to bind to the substrate binding site. You're attacking this point. Proton is moving. You stretch it out. There's a transition state. You're starting to move this. This is the hydrogen is going to come in and attack the nitrogen. It's leaving group. And we form a covalent bond here. Water comes in. It's going to hydrogen bond with the histidine. Oxygen is going to attack that, we'll cleave that bond as we stretch it out, transition state stabilization. Attacking that bond is broken, and now we have the final product leaving, and then we're back to the original string of bond. Okay. And this is another thing that would be helpful to look at. What we have is energy versus reaction coordinate. Here is our enzyme plus substrate, step number 1. when we have the enzyme substrate complex, step number 2. There's obviously a transition between there, even though it's not shown in the mechanism. Then we go to step number 3. We transition to step number 4, and there's a little bump to step number 5, and we're going to find 6 in the next transition state, and then finally we get the enzyme product complex, which then breaks down to form a separate of the enzyme and product. So that may help you in terms